So when we do integration, our integral is based on the Riemann sum. And I want to review the Riemann sum a little bit because even though once we learn the fundamental theorem of calculus, you don't need to go back and actually write out the Riemann sum. But when it comes to applications, you need the Riemann sum to be able to conceptualize what the integral even needs to be. We will do the nice fundamental theorem of calculus of taking the antiderivative at b minus the antiderivative at a, but it's important to understand the process of slicing into a Riemann sum so that any new application that comes your way, if you're comfortable slicing it up and writing that Riemann sum, you can develop the integral yourself without having to rely on a formula. So let's kind of go through the terminology and notation of that Riemann sum. So say we've got some function here, y equal f of x, and we're running from x equal a to x equal b. So I'm going to be doing this from the x perspective. We could have a function of y running from y equal a to y equal b. Similar notation and definitions. It's just the variable would be y in that case. Okay, so remember, what integration tries to solve is if I want to know how much of this function I get over an interval, and what I mean by that would be what is the product of these y values with this change in x. The problem with doing that is the y is constantly changing, right? So the basis of the Riemann sum is, well, let's pretend that y is not changing over small subintervals here. And then we'll let those subintervals shrink. That's the basic idea of Riemann integral. So before we shrink things, though, we have the Riemann sum. So the first step is to partition that interval. So we're going to cut this thing up into subintervals. And we typically, these are all x values, right? So this a we subscript as x sub 0. It's the first x in our subdivisions. And then the next one is our x sub 1, and so on. There would be some k amount of subintervals here. So mine actually has 1, 2, 3, 4, 5, 6 subintervals, but in general there's going to be k of them. So somewhere in here is some x sub k minus 1 and some x sub k. And then by the time we get to the end, this last x value b is x sub n. So I think I misspoke there a second. I want to say that there's n of them. We're going to look at the kth one. So what do I have here? 1, 2, 3, 4, 5, 6. So my n is 6. I've divided it into 6 subintervals. We're going to look at an arbitrary one when we write our Riemann sum. So what we just did there by creating those x values is we created the partition. So that's our first thing. We have to remember that terminology, partition. Often we will just, in the notation, use the letter p. And it's that set of values. So p is, the partition is the x values. Why do we subscript starting at 0? Well, think about it. To have the very first rectangle ends at x1. The second one ends at x2. So the nth one will end at x sub n. So that very first x has to be x0 so that your first rectangle ends at x1, and then that subscript tells you how many rectangles you have. If your last value is x sub 6, you have 6 rectangles. Okay. So that's our partition. And then inside each subinterval, we are going to pick a value, an x value in that subinterval, and we're going to assume the function is constant in that subinterval, and its value is at that value we picked. So for example, let's just draw our arbitrary one here. So I can pick any x value in here I want. There's no limitations in the Riemann sum as to how you pick it. You can even pick the endpoints. So I could pick x sub k minus 1, or x sub k, or anything in between. So I'm going to randomly pick some spot here. And in our notation, we've been using c sub k for that x location. So what is c sub k? That's some point contained in that interval from x sub k minus 1 to x sub k. That little thing I've drawn right there is our fancy set notation for contained in. So c sub k is somewhere in this subinterval. It's a point in the kth subinterval. And now I want to assume my function is not changing, and I will assume that its value is whatever it was at my c sub k. Let me graph that. So what did I just do? I took a function that was not constant, and I'm approximating it with a constant function. Not a very good approximation, right? I mean, at some point it ends up way down here in the negatives, and I'm still just pretending it's a constant the whole way away. So it's very rough in this picture for sure. And so we create this region right here, a rectangle. And so we're interested in, let me label over here on this axis, this height of this rectangle is whatever this function equals at c sub k. So it's f at c sub k. So our Riemann sum is going to involve adding up these little rectangles. So we assume the value of the function over that whole interval. So we know we know the value of the function, f of c sub k. We also need to know how long we're holding it at that value. So we've got y times so much x. Well, how much x do we have? Well, it's however far we went from x sub k minus 1 to x sub k, some change in x. So I'm going to call that delta x sub k. That's the width here. Well, that's just the bigger value minus the smaller value, right? X sub k minus x sub k minus 1. The great thing about the Riemann sum is it does not require us to partition so that all these x's are the same distance apart. All your delta x's do not need to be the same. That's why I'm subscripting. You may recall in Calc 1 we would often say, let's assume they're all the same. And then you can kind of drop the subscript, because delta x would just be your endpoint minus your beginning point divided by how many rectangles you have. But I'm doing the most general case here. We're not going to assume a constant delta. I'm also not assuming anything about where I pick c sub k. If you recall in Calc 1, we would do left endpoints or right endpoints or midpoints. C sub k in general can be whatever you want. Okay, so what is that? I'm interested in that I've got that y value for this amount of x. So I'm interested in that product. You know, probably a classic example would be you're going 60 miles an hour for 3 hours. You've gone 180 miles. Well, if your velocity's changing, if your speed's changing, then this is just an approximation. Just like we're definitely not getting exactly what it would be with that curve, because of actually this velocity would be 0 and then we're going backwards. So, okay, we've got all of our notation here. Now, what is the Riemann sum? So we'll often use an S for sum and an N to indicate N subintervals. And then we want to add up k from 1 to n of all these quantities. So we've just drawn one arbitrary one, but over every subinterval you would have another one of these rectangles that would be some y value for some amount of x. Some y value for some amount of x. There would be n of them, and so we're adding up all n of those. And that is our Riemann sum. That is not the integral. So far, this is just an approximation of what we want. Next, we'll look at how this relates to the integral that we talk about, the definite integral, sometimes referred to as the Riemann integral. So we'll look at that next.